Hello students. So we stopped in the previous lecture at this point where we were discussing the storage properties of aquifers. To begin with, we started by describing or defining the storage property of an unconfined aquifer, which we refer to as the specific yield. And the specific yield is defined as the volume of water released by the aquifer per unit area of the aquifer per unit decline in head, right? So the per unit area that is mentioned in this definition refers to the plan area of the aquifer, right? So, so if you notice this cross-sectional image that I've shown here, the area is referring to this plan view area that would be visible from above, right? So that represents the horizontal area over which this decline in head is taking place. Okay, so the term specific yield does not have any units because it has volume on the numerator, the volume of water released by the aquifer, and on the denominator I have the cross-sectional area, which is units of length square, and again in the denominator I have the decline in head, which is again in units of length. So I have length cube in the numerator and length square multiplied by length in the denominator, and therefore I end up with a term that does not have any units. Now, the specific yield, the typical range of values that it takes is anywhere between about 5%, 0.05 at the lower end, to around 25 or 30%, 0.25, 0.3. Now, the mechanism by which the water is released in an unconfined aquifer is just that the water is draining out by gravity. So I gave the analogy of a sponge that has been saturated with water. If you place it on a table, on a surface, the water that is been saturating the sponge gets released by the from the sponge just by gravity. Okay, but will all the water that is inside the sponge be released? No. The portion of the water that cannot be held back by the molecular forces of attraction between the sponge particles and the water molecules, that portion is released by gravity. The rest of the water that is being held back by molecular forces, which are strong enough to overcome gravity, will continue to remain in the sponge, right? So that is the analogy that you can think of in the context of an unconfined aquifer. It is just the water that is draining out of the pores by virtue of the fact that gravity is a stronger force than the intermolecular forces of attraction between the soil particles and the water molecules. Right? The rest of the water is going to be held back by the strong forces of attraction between the soil particles and the water molecules. So that's the distinction that we will draw between the water that is drained out by gravity and the water that is being held back by the cohesive or adhesive forces of attraction between the particles, soil particles and the water molecules. Okay, so this is the unconfined aquifer. Now we will move on to confined aquifer, right? The definition for the storage property in a confined aquifer is almost identical to that in an unconfined aquifer. So the storage coefficient, or S, is defined as the volume of water released by the aquifer per unit area of the aquifer per unit decline in head. Now this is exactly the same as what we defined for the unconfined aquifer. But when we define the specific storage, which, if you remember, was another property which was defined not as a dimensionless quantity, but as one which has dimensions of length to the power minus 1. When it comes to defining specific storage, the definition of specific storage is marginally different, but it's a critical difference. So the way it's defined is specific storage, SS, is the volume of water released by the aquifer per unit area of the aquifer per unit decline in head. All that portion is the same. And then I add this additional portion per unit thickness of the aquifer. So I'll have an L cubed on the numerator, which is the volume of water released, per unit cross-sectional area, L square, per unit decline in head, L, per unit thickness of the aquifer. So therefore, in the denominator, I have L to the power 4. In the numerator, I have L to the power 3. So therefore, I end up with a term which has dimensions of L to the power minus 1. Right? So that's consistent with the way we've defined SS. Right? It will have dimensions of L to the power minus 1. Now, some people, instead of defining it this way, they define it a little bit differently by saying, what if I have the unit area and the unit thickness? So multiply the area, cross-sectional area, by the thickness, you get the volume of the aquifer, right? So therefore, SS is also defined as volume of water released by the aquifer per unit volume of the aquifer per unit decline in head, right? So it's volume of water released divided by volume of the unit volume of the aquifer, which is the area multiplied by thickness, the same thing as volume, per unit decline in head. That also gives me the same L cubed divided by L cubed divided by L. That would also be L to the power minus 1. Now, the important distinction between the unconfined aquifer and the confined aquifer is in the magnitude of the storage coefficient. We saw in the previous slide that the specific yield ranges between around 10 to the power minus 2, that's the higher end, 0.05, sorry, the lower end, 0.05, to about 10 to the power minus 1, 2.5 to 10 to the power minus 1, or 3 into 10 to the power minus 1. That's the higher end of the specific yield. When it comes to the confined aquifer, the storage coefficient is much, much smaller. At the higher end, it may be as high as 10 to the power minus 3, but at the lower end, it's about 10 to the power minus 5, which is very, very small. So now these parameters, if you notice, even the best case scenario for a confined aquifer, which is 10 power minus 3, is about 10 times or 100 times smaller than for an unconfined aquifer. And the worst case, 10 power minus 5, is about 1,000 times or 10,000 times smaller quantity as compared to the unconfined aquifer. Now, obviously, there's a question that comes up in our mind. Why is the storage coefficient so different between a confined aquifer and an unconfined aquifer? And the explanation for that is the process by which the water is released from the storage. Right? In the case of the unconfined aquifer, we just mentioned that the water is released by gravity. But in the case of the confined aquifer, the process by which it is released is a little bit different. So I'll just describe it in a sentence, and then I have a long derivation that I will do, which will establish the case more strongly. So the explanation for the release of water from a confined aquifer is that the water is released from storage by a combination of, number one, compressibility of the water, number two, the compressibility of the aquifer, right? So the act of extracting water from a confined aquifer is done by releasing water from storage through a combination of the compressibility of the water and the compressibility of the aquifer. Okay, now obviously water is, for all practical purposes, water is very close to being incompressible. But in the limit, it does have a little bit of a compressibility, and that little compressibility plays a role in the confined aquifer. So the water gets released from storage by compressing the aquifer and compressing the water a little bit, right? So we are going to go through a long elaborate derivation for this. You don't have to memorize this. It is just for information and to give you a theoretical understanding of the release of storage in confined aquifers. So let us consider a confined aquifer. I'm going to just draw standard confined aquifer under the land surface. So this is the top of the confined aquifer. This is the bottom of the confined aquifer. Here I have the land surface. And at the land surface, you have trees. You may have some buildings. All of that is going on at the top of the land surface, on the land surface. And then at the below that, invisible to the human eye, you have a confined aquifer. Now let us consider an imaginary surface in this confined aquifer. Okay, just consider an imaginary surface at some point inside this confined aquifer, and we will zoom into that imaginary surface and look at what is happening. So I'll draw that here over here. So let's imagine this imaginary surface, and let's imagine the soil particles that are at this surface. Okay, now of course I'm blowing up this picture. I'm just zooming into the to individual soil particles just to make the point. Okay, so there's the soil particles arranged at that surface, and there is the water that present between the molecules, the soil particles in the intergranular voids, right? And please remember that this is a confined aquifer, and all the voids are completely filled. So there is no all the pores are completely filled with water. Okay, all right. So now, if you think about it, this imaginary surface that I have drawn in the confined aquifer is experiencing some stress. Okay, it is experiencing a stress due to all the material that is present above it, right? So if you look at this imaginary line, there's a lot of soil and trees and buildings and all of that on the land surface. The weight of all of that is acting down on this imaginary surface, right? So this portion that is above this imaginary surface, you can call it the overburden, right? So this overburden is acting downwards, and if you think of uh, the stress that is acting on this surface, I'm going to denote that by sigma t. And that is the total stress acting on this imaginary surface due to the overburden that is present above it. And the overburden includes everything that is above this line, right? All the soil, all the rocks, all the buildings, all the trees, all the human activity on the land surface, all of that combined results in one stress that is acting downwards at this surface. Now, if this surface has to be at equilibrium, there has to be some counteracting force or counteracting stress, uh, which is negating the impact of this overburden. What could be that? The resisting stress is the intergranular stress between the soil particles, which is resisting this overburden pressure, right? So there's the intergranular stress in the soil molecules. I'll refer to that as sigma S, which is the intergranular stress between the soil particles. And then there is also the pressure of the water inside this uh, in this aquifer, in the confined aquifer, right? So these two, sigma S, the intergranular stress, and P, which is the pressure of water inside this, these two combined are resisting the, the stress that is acting downwards from the overburden, right? So mathematically, if I want to express that, I can say sigma T, the total stress overburden stress, is equal to sigma S plus P. Okay. So if I differentiate this once, I will get d sigma T equal to d sigma S plus dP. Okay, let's just keep this aside and look at this. Now imagine that I have, let us say I have a small elemental volume here at this surface. Okay, I have a small control volume at that imaginary surface, which has a cross-sectional area of delta A and a thickness of delta Z. Okay, so let's say the volume of this box, delta V, equal to delta A times delta Z. Let's imagine this. Okay, now suppose I remove a little bit of water from this imaginary box that I have drawn there. Okay, imagine that I'm taking out a little bit of water from this box. What will happen to the pressure of the water inside this box? This box has got water inside it at a certain pressure. I remove some water from this, so it will reduce the pressure of water inside that box, right? But when I do this, is there going to be any change in the overburden pressure from above? When I remove a little bit of water, all the soil and all the material above this box, it's not going to change. It's going to remain the same. So sigma t is not changing. So in other words, d sigma t is 0 when I do this. So let's write this 0. When I remove a little bit of water from that box, the total overburden pressure does not change. It doesn't change at all. So d sigma t is 0. So that's equal to d sigma s plus dp. So when I rearrange this equation, I get a very interesting finding. D sigma s equal to minus dp. Now this is something very interesting and important. Oops, sorry. Now what this equation is telling us is that when I remove some water from this confined aquifer, it reduces the pressure of water in that aquifer. But a reduction in pressure, whatever that amount is, if dP is the reduction in pressure, it has to be accompanied by an increase in the intergranular stress in that particular uh, uh, little control volume, right? So if dP is negative, right, d sigma s has to be positive, right? And if dP is positive, then d sigma s will be negative. So you can think of it also as, if I add some water inside, the pressure of water will increase and the uh, uh, intergranular stress will decrease. D sigma s will become negative, right? So whether I'm pumping water out or pumping water in, the response will be the response of the intergranular stress and the water will be opposite to each other, right? So that the total stress remains same. When I add some water inside, that also does not change the overburden pressure. When I remove some water, also it does not change the overburden pressure. So the impact of removing a little bit of water is a reduction in the pressure in that confined aquifer and an increase in the intergranular stress between the soil particles. Okay, so now this is very important. So please keep this in mind. Now, when I increase the stress, intergranular stress, that will result in a slight compression of the aquifer, right? If I increase the stress, what happens? It gets compressed a little bit, right? And it's a normal stress, so it'll act it'll act to compress the entire volume. So let us try to look at what is the compressibility of the aquifer, or how do we define compressibility? Compressibility of the aquifer. Now you might have studied about this in strength of materials or in earlier courses in your BTech. Compressibility is defined as alpha equal to minus d delta V divided by delta V divided by d sigma s, right? What is the change in volume per unit volume of that material per unit increase in stress, right? So that's what this is telling us. And there's a negative sign to indicate that when I increase the stress, the volume will decrease, right? So delta V is the original volume of this aquifer, of that little box that I had drawn. I'll draw it again over here. Let's imagine this little box with a cross-sectional area of delta A, that's plan area, and a thickness of delta Z, and delta V is simply the cross-sectional area multiplied by the thickness of that. Okay, so d delta V is the change in the volume due to this additional stress that is acting in the intergranular the soil matrix. Okay, so now delta V, as I said, is delta A, I'm sorry, times delta Z. Now I'm going to differentiate this. So d delta V equal to delta A times d delta Z. So what we are assuming here is that when this compression happens, the cross-sectional area, the plan view cross-sectional area of this box does not change, only delta Z changes. If it gets compressed, it happens due to a reduction in the delta Z, but delta A does not change at all. Okay, that's the assumption that we're making. Now, if you combine these two, you will find that it is d delta V divided by delta V is equal to d delta Z divided by delta Z, right? So therefore, if I replace this d delta V divided by delta V in that definition, I'll get alpha equal to minus d delta Z divided by delta Z, the whole thing divided by d sigma S, right? And of course, if you go back one more slide, you remember that d sigma S is actually minus dp. So if I replace this d sigma S over here with minus dp, I eliminate that negative sign over here. So I will get d delta Z divided by delta Z equal to alpha times dp. Okay, so this becomes an important equation for us. Okay, just keep this in mind. So d delta Z divided by delta Z is equal to alpha times dp. Okay, now let's just imagine what happens when the aquifer gets compressed. When the aquifer is compressed, how is this compression? What is the process by which it's getting compressed? The porosity of the uh, of that little box, the porosity inside that box is going to change, right? The soil particles are going to get rearranged a little bit in such a way that the porosity of the of that box is reduced by a little bit, right? So when the aquifer is compressed, soil particles get rearranged by a, a slight reduction in the porosity, right? So the porosity gets reduced, and in that process, the aquifer gets compressed. The soil particles rearrange themselves in such a way that the porosity marginally gets reduced, and this results in the compression of the aquifer. So then let us think about the total volume of inside that aquifer is the volume of solids plus the volume of water. Right now, this we have already we're already familiar with this, right? So d delta V equal to d delta Vs plus d delta V W, right? So we are just simply extending what we already know. But what is delta Vs? What is the volume of solids inside this particular uh, box that we have drawn? It is the total volume delta A times delta Z multiplied by 1 minus n. Does that make sense? The total volume multiplied by 1 minus porosity. Porosity is the volume of voids. If I do 1 minus n, I get the rest of the volume, which is the volume of the solids. Delta A times delta Z is the total total volume, and 1 minus n is the percentage that is not the voids. So therefore, delta Vs must be delta A times delta Z times 1 minus n. So if I differentiate this once, keep in mind that my delta A is not changing in this whole process. The only thing that's happening is delta Z is getting reduced by a little bit. And now we will see that, as I already said, porosity is also going to change by a marginal amount. So if I were to write that mathematically, it will be 1 minus n times d delta Z minus dn times delta Z. Right? I just applied chain rule. Delta A is a constant, so therefore that doesn't get differentiated. The remaining two terms are 1 minus n and delta Z. So 1 minus n times d delta Z minus dn. 1, of course, is a constant, so it doesn't doesn't contribute anything, minus dn times delta z. Now this term must be equal to 0. Do you agree with that? It must be 0 because the total volume of solids that's present inside that box is not going to change. It is just getting rearranged by a reduction in porosity, but the total volume occupied by those soil particles is not changing. So therefore, this d delta Vs, the change in the volume of solids due to this compression, is not going to be there's no change in the volume of solids itself. It is the rearrangement of the particles by reducing the porosity that is causing this compression. It is not, the volume of solids cannot change. The total number of particles before and after is the same, and the volume occupied by those particles is still the same. Now, what has happened is that in this compression, the porosity has changed, so the volume of voids has reduced, and therefore you're getting the same particles arranged inside that same box in a slightly different configuration by uh, reducing the porosity. So if you rearrange this equation, you will get it's equal to 0. So then I will get 1 minus n times d delta z equal to dn times delta z. Of course, so if you rearrange this, you'll get d delta z divided by delta z equal to dn divided by 1 minus n. Right? And we just, in the previous slide, we just found out that d delta z by delta z is nothing but alpha into dp. So if I replace this with alpha into dp, I will get alpha equal to dn divided by 1 minus n times dp. Now this is another equation that we are getting from this, right? So this is just a combination of what we got in the previous slide, d delta z by delta z equal to alpha times dp. Put that in here, rearrange it a little bit, you get alpha equal to dn by 1 minus n multiplied by dp in the denominator. Okay, so just keep this in mind. So this is telling us that this compressibility of the aquifer is happening by a combination of change in the pressure dp and a change in the porosity dn, which is resulting in this compressibility of the aquifer. Now we will look at the compressibility of water. Now, in terms of the definition of compressibility, it's the same, beta equal to minus d delta Vw divided by delta Vw divided by dp, right? How much did the volume of water change per unit volume of water, and what was the pressure or the stress that caused this change in volume? So that's how we define compressibility. Now, this is something that you must have studied in your earlier courses. So please go back and refer to those for the definition of compressibility. We'll just move on from here. Now, remember that mass has to be conserved in this entire process. And although most of the time when we discuss conservation of mass, we discuss it in the context of incompressible fluids, right? Especially civil engineers, we don't discuss much about air and other gases, which of course can change their density and so on. When we discuss water, in most situations, we discuss it from the point of view of water being assumed to be incompressible. But in this particular circumstance, in a confined aquifer, the compressibility of water also plays a role in this. So therefore, we will have to write it up as follows. Rho times delta Vw is a constant, right? Density times volume is a constant. That's the way of writing that. So if I were to differentiate this, I would get d rho times delta Vw plus rho times d delta Vw equal to 0. Right hand side I have a constant, you differentiate that, you get a 0. So again, if you rearrange this, you'll get d delta Vw divided by delta Vw equal to minus d rho minus d rho divided by rho. So now I'm sure you already know where this is going with respect to how we are rearranging this. So in other words, if I put this into this equation, this negative sign disappears because I have another negative over here. So I'll get beta equal to d rho divided by rho divided by dp. Now we have to be a little bit careful here because all of these terms look very similar to each other. There's a rho, there's a p, there's a beta. Right? This d rho refers to the change in the density of water. dp is the change in the pressure of water, and beta is the compressibility as we have defined it. So if I rewrite this, I can write this as d rho equal to rho times beta times dp, right? Now we've got these different expressions um, to indicate the compressibility of the water inside this. We've written it in terms of the what is the change in the density of water due to this compressibility and the change in the pressure that is accompanying this or that is causing this compression of the water. So now the mass of water in the elemental volume. So my control volume has a little bit of water in it. What is the mass of water inside that box? So it will be delta M. If delta M is the mass of water in that box, it will be rho times N times delta A times delta Z, right? Rho is the density, N is the porosity, delta A times delta Z is the total volume. So N times delta A times delta Z is the volume of voids multiplied by total fraction of the volume of void multiplied by total volume. So that gives me the volume of voids itself multiplied by the density of water. That gives me the mass. Now, what I'm going to do is to differentiate this, and you may already be able to guess where this whole thing is leading towards. So now remember, rho is not a constant, n is not a constant, delta z is not a constant. The only constant in this is delta a, so we'll keep that outside. And then we're going to apply chain rule to the remaining three terms. So we will get rho times n times d delta z plus d rho times n times delta z plus rho times dn times delta z. Okay, so I hope that's fairly clear what we have done over here. So now what I'm going to do is I see there are some constant terms across these different. So let me rewrite this like this: d delta m equal to, I'm going to take out rho common and delta z common. So I'll get rho times delta a times delta z. Rho has come out here, so it will be n. There's no delta z here, so I'll have to divide this d delta z divided by delta z. There is no rho here, so I'll have to write this as d rho by rho times n. Delta z has gone out common, okay, plus rho has gone out, delta z has gone out, so I'll be left with dn. I hope, yeah, looks correct. So that is equal to rho times delta v, because delta a times delta z is nothing but delta v, times, now let us try to go back and write everything in terms of alpha and beta. So I have d delta z by delta z, which if I go back, d delta z by delta z, I've written it in terms of dn by 1 minus n. That's one way of writing it. Alpha times dp, that's another way of writing it. So let us write it in terms of alpha and dp. So d delta z by delta z is alpha times dp. So this would be n times alpha times dp plus d rho by rho, which we had over here, which is beta times dp. right? B rho by rho is beta times dp. So it will be n times beta times dp plus dn, which again we wrote it somewhere over here. It's alpha into 1 minus n into dp, right? dn, you see over here, dn is alpha times 1 minus n into dp. So let's just go back and write that alpha times 1 minus n times dp. Now, if you look at all of this, I see an n alpha dp, and then here I have a minus n alpha dp. So those two terms will cancel out. So I will get d delta m equal to rho times delta v times there's an n alpha dp minus n alpha dp, that's gone. Uh, I will have alpha plus n beta whole thing multiplied by dp, right? I hope this is making sense, right? So d delta m is rho times delta v times alpha plus n beta times dp. So if I rewrite this again in this form, d delta m divided by rho delta v equal to alpha plus n beta times dp. Okay, we will just carry this forward to the next slide and then continue from there. So it's d delta m divided by rho times delta v equal to alpha plus n beta times dp. Okay, so let us look at the left hand side, the term that we have on the left hand side. I have a d delta m, which is the amount of water that has been released from storage, right? The mass of water released from storage divided by the density of water rho. So the mass of water released from storage from the aquifer divided by the density of water, mass kg divided by kg per meter cube, will give me the volume of water released from storage by the aquifer. So this is volume of water released from the aquifer. And in the denominator, I have a delta V, which is the volume of the aquifer, the original volume, right? So it's the volume of the aquifer is equal to alpha plus n beta times dp. Okay, so the left-hand side is simply the volume of water released from the aquifer divided by the volume of the aquifer. On the right-hand side, I have alpha plus n beta multiplied by a dp. Now, at that imaginary control volume that I had drawn, let us write the total head. I'll just write it over here. The total head H, piezometric head, if you remember, is P by rho g plus Z. At that point, this is the um, uh, the total head. Now, when this water gets released from storage at that particular point, there is going to be a change in the total head, right? So how much will that change be? Let us differentiate this. So I'll get dH equal to dP by rho g plus dz, but at that particular point, there's no change in z, right? The elevation of that point is not changing. So there's just dH equal to dP by rho g. So if I replace this dP over here with rho g times dH, let me just do that. All I'm doing is removing this dP and replacing it with dH. There's also a rho g. Keep that in mind. So now look at this equation. I have volume of water released from the aquifer divided by the volume of the aquifer, and then there's a dH on the right hand side. If I bring that down to the denominator, I will get times dH. Then I'll get rid of the dH over here, right? So what is it? What is this that I have on the left hand side? It is the volume of water released from the aquifer per unit volume of the aquifer per unit decline in head. which in other words is nothing but my specific storage. Specific storage. So the way we define specific storage is this left-hand side, and that we have found out now is equal to rho g times alpha plus n beta. So we have just established now that this specific storage is nothing but a term that involves both the compressibility of the aquifer and the compressibility of the water, right? So the mechanism by which the water is being released from storage is by a combination of these two processes, where the aquifer gets compressed and water gets released from storage. And in this compression, there is a marginal change in the porosity of the aquifer. So all of these factors are reflected in that term on the right hand side, where you see it's alpha plus n beta. So alpha is the compressibility of the aquifer, beta is the compressibility of the water, and n is the porosity of the aquifer. And rho and g, of course, rho is the density of the water, and g is your acceleration due to gravity. So this is what we have established by going through this entire derivation. Again, as I said, there is absolutely no need for you to worry about memorizing this kind of a elaborate derivation. So don't worry about it. But this is just to explain to you the processes that are at play. Now, if I were to integrate this, I, I derived this entire thing for that little box in that imaginary control volume. So suppose I integrate this over the entire thickness of the aquifer. What will I get? I will get S, which is my storage coefficient, equal to rho g times alpha plus n beta multiplied by B, the thickness of the aquifer. So that would be the other parameter of interest. How do I obtain this? Simply integrate over the thickness of the aquifer. So how do you go from here to here? So integrate over aquifer thickness, you get this. Okay. So now, so this establishes mathematically why the storage coefficient of a confined aquifer is very, very small compared to the specific yield of an unconfined aquifer. There, the process by which the water is released is draining out by gravity. And here, in the case of the confined aquifer, it is due to the compressibility of the water and the compressibility of the aquifer. So therefore, naturally, the water is not highly compressible, the aquifer is not highly compressible. Therefore, the amount of water that gets released is very, very small. Right. So this is a kind of a combined mathematical and physical derivation for that explains the the uh, uh, the the difference between the storage parameters for an unconfined and a confined aquifer. Now, what is the physical implication of this? What we are saying is that when I pump water out of a confined aquifer, right, my aquifer is getting compressed, okay, and the water is getting released from storage. Now, imagine doing this over a long period of time. I keep taking water out of a confined aquifer. The aquifer keeps getting compressed and compressed and compressed, and that the volume of the aquifer becomes a little bit smaller over a long period of time. If I keep doing this, the physical implication of excessive pumping, right? Whatever I've done so far is giving you a mathematical and a physical understanding uh, uh, from the point of view of the compressibility. But the implication of this entire exercise, the physical implication is that when the aquifer gets compressed, right, the entire land surface subsides, right? There is a subsidence in the land surface. So there are some very drastic examples from around the world. These two pictures that you see over here are from the San Joaquin Valley in California, where you can see in 1955, the land surface was somewhere over here, Right, in 1955, the land surface was at this elevation. In 1977, about 20-22 years, there has been a subsidence. There's a card that's being held up there. What does it say? Subsidence 9 meters from 1925 to 1977. Okay, so there's a human being standing there, so about 1.82 meters, and then you can see how much the land has subsided due to intensive pumping over a period of time. Here again, on the other side, I have a subsidence of 6.2 feet from 1988 to 2016. So this phenomenon is not without its, there's a physical implication. When you pump water from a confined aquifer, it's it causes this tremendous uh, uh, land subsidence, and that is one of the most important physical implications of excessive pumping. Now, you may ask the question, well, if it's causing this kind of excessive land subsidence, why don't I just do the opposite? Why don't I pump water in, which will cause the subsidence to be reversed, right? Suppose I have some wastewater. Let us say I take some wastewater, treat it satisfactorily to some extent, and then pump water into the aquifer. Then it will won't it just reverse the process, right? When I pumped water out, it caused compression of the aquifer. When I pump water in, it will do the opposite. It will cause the expansion of the aquifer, which may bring the land surface back. Now, that is true. Mathematically speaking, it's true. But the unfortunate thing is that this process of compression of the aquifer is not an elastic process. It cannot, I mean, to a certain extent, it might be reversible, but beyond a certain point, this process is not reversible. So whatever land subsidence has happened, pushing in or pumping in water or injecting water at a high pressure into the aquifer can only very marginally, within the elastic limit, you may be able to recover a little bit, but there's no reported global instances of pumping water in, which has caused land to come back up. To the best of my knowledge, there hasn't been any reports. So feel free to go online and look for evidence if anybody has reported of this reverse process of when you pump water back in, are we able to make the land recover from its subsided state, right? So that process is not it's not a reversible process. So that's something that you have to keep in mind when you look at this process. Okay, so I will stop with that. So this recording is to take care of Tuesday's lecture, which I will not be able to deliver because I'll be traveling. I will be reaching Chennai on Wednesday morning. I won't have enough time to travel to Tirupati before the lecture on Wednesday morning at, I think it's at 9 o'clock. So I won't be able to make it by that time. So Wednesday's lecture will be online. I'll deliver it online from Chennai. Okay. So this lecture is for Tuesday's lecture. This recording is for Tuesday. Wednesday's lecture we will meet online, but instead of being outside the country, I'll be in Chennai. And then Friday's lecture, by that time I'll be back to campus, and so we will meet in person on Friday. So see you all on Friday in person, and then on Wednesday virtually, but separated by a much smaller geographic distance. Okay, so take care very much, and thank you. See you all soon. Bye.